All right, I think we're here. We're going to look at a new thing today. It's going to be more of a statics topic than it's strength of materials, although it will lead into some new strength of materials stuff later. But what we're going to do is look at trusses. So we're going to stick with two-dimensional trusses for the time being, and that's just going to be simpler to start with. We'll look at a new thing called moments. You know, we've had the summation of forces in X and Y and even Z. Those all had to equal 0 so that our object, our body, wasn't translating in any direction. But we also need it to not be spinning around some other point. In order to do that, we're going to need this idea of a moment. So we'll add that in today. Also, just a note. Quiz 1 opens today, and you have 3 days to finish it, so it's not a lengthy thing at all. I think there may be 5 to 10 questions on it. I didn't look, but they're the simpler, more direct questions. So what I would do with it is I would take Quiz 1 like an exam, so that you kind of get a feel for where you're at with the base level problems. And what I mean by like an exam is just a calculator and the quiz. No MathCAD, no looking back at notes and stuff like that. Although you can totally go do that. If you get stuck somewhere, then go back, break out MathCAD or whatever. You're not going to be able to do that on the exam, the actual exam one. But for the quiz, if you get stuck, you can look all that stuff up. But I would treat it like an exam to see where you're at. All right, and that opens today, or it should be open now, I assume. Yeah, nobody's attempted it yet. It does have a password, although there's the password right there. And it'll be due on the 16th at midnight. Homework 7. So we will skip over homework 6 for a few days. Homework 7 opens today, and it has to do with these trusses that we're going to talk about. Before we do any of that, we're going to go back a little bit and work on this problem here. So this is a web work problem that has to do with some shear stress. Well, it might have, it's got several stresses in here. We won't solve all of these, but we'll kind of get through the idea of what we're doing on this. So how about, let's see, there's nothing up there. How about we copy this and put it over in OneNote. So all of this, we're not going to do all of this, but we need something to start with. So let's paste it. All right. So this is a little block that's got a yoke and a T. I don't know what the technical terms for these particular things would be, but it's it's a joint that's made to slide together in one way, in the Z direction I would call it, but not come apart in the X or Y direction. And the force is in the X or Y direction. Probably the Y direction is what it looks like. So we've got a bunch of dimensions here. They refer to all these L's and W's on the drawing. And the assembly shown is symmetric about the line along which force F is applied. So it's a mirror image of one half versus the other half. That's fine. The parts are close fitting. So in other words, it does show a little gap around here, but close fit means that there is essentially no gap. So even though it shows one, that's just for the picture. Find the following stress values if the joint is loaded with 30 kips. So if you have 30 kips here, and the reaction 30 kips over here to keep it from translating around. For each case, make a sketch that illustrates the stress area. Okay. Normal stress in the stem. So the stem it's even labeled stem. Stem of part 1 and part 2. I don't want to do those because I assume those are pretty straightforward. I will draw the area on top of here just to make sure that we're on the same page. But here's the area for the normal stress in the stem of part 2. In stem of part 1 would be the same thing, but it's a little bit bigger, right? Or at least it looks bigger in the picture. These, C and D, those are the ones that might be more useful to us. So the shear stress, all right, let's get rid of this area that we drew on here. The shear stress in the tabs of part 1. So the tab being here, the shear stress in there. So we have to kind of think about shear failure means that the force causing failure is going to be on this plane of failure. So there are two pieces. We'd have this area and the corresponding area over here, which is going to be hidden, at least part of it's hidden, over here. So what that would make happen is the two little blocks there called tab would actually shear away from this. So why don't we draw part 1 in its fractured state according to this kind of failure. It's going to be kind of, I don't know, clumsy to draw this maybe. Let's just kind of sketch it out over here a little bit. We don't need to spend a whole lot of time trying to make it perfect. And that. So what's missing is, these little tabs are gone. So they were right here and right here, but they have been sheared off. So they're over here somewhere. Tab piece here and a tab piece over here. Those have sheared off, and they sheared from, this area here and this corresponding area on the back side of this that, we can't see it. So the shear stress or the shear force would be on this little surface and on this surface. I just realized I've got the chat covered up, so if anybody's typing anything, I can't see it. Let me move it. There we go. Nobody typed anything, so it's fine. So this shear force is going to be, there are two forces here. Here's our applied external force, and for me it was 30 kips. So each one of these shear forces is 15 kips. So remember, a kip is 1,000 pounds. Let's see, what else? So the area is labeled as, I don't see the thickness on here. Oh, it's H. It's kind of covered up in all of this stuff. So H would be this dimension, and this dimension is labeled as L4. So L4 for me is 1.6 inches and H is 1.32 inches. So the shear stress would be, let's write the equation. Tau for shear stress equals the shear force over the shear area. The total shear force, if I combine both of these, is 30 kips. So let's write that as 30,000 pounds. And the area, I have two of these blue areas, one here and one back here. So each of those areas is a height of 1.32 inches and a width L4 of 1.64 inches. And so our shear stress should be, let me get my calculator set up right. 1.32 times 1.64 times 30,000 divided by that denominator is 6,929. Those units would be pounds per square inch, so that's PSI, or 6.93 KSI. Hopefully that's actually the right answer. I didn't check that, so let's just check. Let's show the correct answers. Gotta log in. There it is right there, the 6929. So we were right. To do the next part, let's actually go in and let's see which one is delete. Don't remember. Let's get rid of all of this. There we go. So to do the next one, part D, the shear stress in the tabs of part 2 would be similar, and we won't solve it, but the tabs are, they're right in here. This area, and then there'd be another one back on the other side. Both tabs would have to fail. So it'd be the same thing, 30,000 pounds over an area that's H tall, 1.32 inches, times L3 wide, 0.47 inches. So it would just be 30,000 divided by 2 areas of 0.47 times 1.32 inches squared. So that's all that would be. This type of problem with the 6 different parts to it is not on the exam necessarily, but any one of these 6 parts would be a problem on the exam. Let's see, the bearing stress between part 1 and part 2. So you got to think about, where are these 2 pieces trying to press against one another, and it's going to happen right here. So that surface and the one that's back there, that's those 2 surfaces, which are W3 by H area, and there's 2 of them. Those are being pressed against this part 1 tab. So it's where the 2 tab areas are pushing against each other. That's the area. It's a bearing stress, so it's actually a sigma compression. It's a compressive stress bearing against each other. And the force would be 30,000 pounds total. And then there are 2 areas, each of which are the H variable times the W3 variable. And that would give you pounds per square inch of bearing stress. And then, finally, the normal stress in part 1, so that's the lighter gray part, at the cross section indicated by the dotted lines. So this one is, the dotted lines are, here, and then there'd be one back there. So what we would do in that case, we might draw this one. We would, let's just draw a top view. We don't need 3D for this. Well, it's not that thick. Something like that. Where this line right here is right here, and this line is right here. So it's, somehow it's a normal stress. It's not a shear stress because the force is perpendicular to these areas that we're talking about. The area being right here and the corresponding one on the other side of the part. So that one would just be force, 30,000 pounds, divided by the area, where the area is the height of H, and there's 2 of these. And you have to do a little bit of math to figure out what this dimension is, because it's not directly given. So you have to do a little bit of, figuring out what that dimension actually ends up being. So I thought I did have a question about this one. And so I thought I'd do a little bit of, how might you go about solving this one. It's not that it's there's any particular trick inside of it or anything. It's not trying to hide any information. There's just a lot of little pieces to work through. The biggest thing with these is taking the different, types of failure that they're describing here and envisioning or even drawing. In fact, this one says to make a sketch that illustrates the stress area. But envisioning what it would look like if it failed in some idealized way. So don't worry about it being jagged or rough or anything like that. If it failed on this perfectly flat plane, what does that plane look like? Because that's the plane that's going to define the area in your stress equation. And then what force is on that plane, because that's the numerator in your stress equation. And is that force perpendicular to the plane or parallel to the plane? And that will tell you if it is a normal stress, perpendicular, or a shear stress, and it's going to be parallel. So you can get a lot of information if you can correctly envision what the idealized failed part will look like. All right, so that gets us kind of a review of the stresses that we did last time. And at this point, I think we can go into the idea of trusses. And for now, like I said, we're going to do two-dimensional trusses. So they exist in a plane. All that means is that these are planar trusses. You could certainly have trusses that are all different shapes in multiple dimensions all at the same time. But ours are going to be planar, because that is not an uncommon thing. It's just it does simplify things where we don't have to deal with three-dimensional stresses. So there's a couple of assumptions that we're going to make to define what a truss is. So one of those assumptions is that for us, we're going to stick with planar trusses. That's not really an assumption. That's just a constraint that we're going to deal with. Some assumptions are that trusses are made or constructed, whatever you want to say, of rigid, and then we're going to call them members. So I've got a little sample truss over here somewhere, and so these little pieces, that would be a truss member, and the whole thing that's the simplest truss you can make with just one single triangle. The whole thing is going to be a truss. So this is a member, this is a truss. Wait, we don't need that anymore. We need that. The next thing is that these members are connected by frictionless pins. Now, in our one here, the pins would be, these little circle, they kind of look like pins. Some trusses actually do have bolts or pins like this. A lot of times you might see a truss and there's like this plate called a gusset plate that's over all the connection points. That is obviously not a pin. It doesn't let things rotate around it, but it's serving the same function as the pin, and that's how it gets built a lot of times in the real world. But we're assuming when we analyze the truss, whatever the configuration is in the real world, we're modeling it as a frictionless pin. And these pins are called the joints. So you have members connected by pins at joints. Forces. So I'm showing a force here with this little brown arrow, and there would be a force here. This is a roller. This is a pin connection. This is how these two things are modeling how it's connected to the ground. We'll talk more about why a roller and a pin later. But the forces are only applied at the joints. Now, obviously, when you have a truss and it's turned into a bridge or whatever, cars are driving across it or whatever, and you might think that, well, at some point there has to be a force, on this piece here somewhere, and not just at the joint. But a lot of how it actually works is the forces are transferred over to the joints. And so when we analyze the truss, we don't put any forces on the joint. So I wouldn't come in here. I had another little arrow. Let's see if I can. Here it is. I wouldn't come in here and put a force on the joint itself. That turns it into a frame at that point, which we'll do frames later. But if I want to analyze it like a truss, then this force has to be taken into account by putting it at a joint somewhere, or maybe dividing it up and putting part of it here and part of it at this joint. So I can't put the force directly on the member anywhere. I have to put it only at the joints if I want to analyze it as a truss, which is what we're doing right now. So I will make the note that you can split forces and apply at joints. So you can do that. So maybe the member itself weighs a whole lot and you have to deal with its weight, the weight of the piece. So what you would do is put half of its weight at one end and half of its weight at the other end where the joints are, instead of putting some sort of distributed load across the member. That brings up another point, or implies another point. Each member only has 2 pins. So I don't have any member that has 3 pins like this. So this piece has a pin that would go here, and a pin in the middle, and another pin over here. This piece couldn't go in a truss. This piece would have to go in some sort of frame or machine or something like that. So when I'm analyzing something like a truss, every member is only connected to all the other pieces in the truss by 2 pins, one at one end, one at the other end. And there's not any pieces like this one where this member has 3 connection points. So each member only has these 2 connection points. Let's see if there are any other important things. Forces are only applied at the pins. Each member only has 2 pins. Each member is rigid. This one is not really an assumption, but it's what happens when all of these things are true. And each member is a 2-force member. And so what that means is, let's just pick a member. Let me turn this fan off, it's kind of noisy. Each member has these 2 pins, one at one end, one at the other end. And we haven't really talked a whole lot about how you model reactions at pins or anything like that. But what you do is each pin has an X and a Y reaction on it. So maybe this is pin A, so this could be AX and AY. This could be point B, so this would be BX and BY. So that's how you would model it if you didn't know anything about this idea of a 2-force member. Once you know that this is a 2-force member, which all members in a truss are 2-force members, they're either 2-force members or this thing called a 0-force member, which means it has 0 force on it. We'll get to that later. So if I know that this member is a 2-force member, I can take the same member, and instead of doing AX, AY, BX, and BY, I can just do the force in AB. And there's your 2 forces. 1 force, 2 forces. They're the same magnitude and opposite direction. So I've drawn this one in tension. The arrows are pointing away from the body. But they could either both be in tension or both be in compression and the same magnitude. So what that does is I went from having 4 unknown values, AX, AY, BX, BY, into 1 unknown, FAB. I just don't know. I don't know its direction necessarily. I don't know that it's in tension or compression unless I can visualize that or solve for it later. But I know its magnitude and its direction. And its direction is, if you connect the dots between the pins, I do know that that's the line of action for the force. And it doesn't matter if this member is some weird shape. I still connect the dots and put the force on that line of action. We'll make this one compression. So it doesn't matter. Now normally, most trusses, and probably all the trusses that we'll do, are going to have straight members, but technically it doesn't have to, although that does create some new issues in buckling and things like that that we're not going to really pay attention to. So we're going to stick with these straight members like this one. But technically, they could be any shape, and that direction for the line of action for the two forces would be defined by the two pins that hold the member in place. All right. I think that gets us the intro to trusses. Now we need to do a little bit of talking about moments. Now, moments should be a review. You should have done a little bit with moments already, either in physics or a previous engineering class, but just in case, just to do a quick review of what we're talking about here, let's talk about moments first before we get into calculating anything with these trusses. So up until now, we had systems where we had two cables and some weight. There was tension in the cables, gravity was pulling down on the weight, and we had all these lines of action, and they all met at a single point, and we had a concurrent force system. That's not going to be the case all the time. There will be other times where you don't have a concurrent force system. Now, inside the truss, if we have each one of these be two force members, no matter how we arrange the truss, each joint is going to be a concurrent force system. But there's a little bit we have to do before we get to looking at each one of the truss pieces individually, because we don't know what's going on here at this reaction or here at this reaction. We need to do that first before we can necessarily look at all the little pieces. So why don't we take and just look at this. So not a truss, but just a beam. And let's put and this is a beam, so we can put the force anywhere we want to. It's not a truss anymore. Let's just put the force there. So let's go to a beam momentarily, and then we'll go back to trusses. So we've got this beam. I put this is my symbol for a roller, so it's got little wheels on the bottom of it. And this is my symbol for a pin, which is just kind of like a triangle. So here's the roller. I'm going to draw it with a wheel. Here's our pin. I'm going to draw it kind of like a fulcrum or something on a seesaw. We have this force. Let's give it, 250 pounds. And let's put some dimensions on here. 1, 2, 3, 4, 5. Let's make that 6 feet. And this can be 3 feet. And what we want to know is this is not a free body diagram because it's not free. It's still connected here and here. So it's not a free body diagram. It's just kind of a sketch or a drawing or something. So we want to make this thing into a free body diagram, which means we need to take, this way. And we need to remove all of these connections here and here. So it's free now, but we need to replace those connections with some kind of force. What was this roller and this pin doing? So again, that's the roller. That's the pin. So the roller, what does a roller do? It's named a roller because it's kind of like a roller skate, that it slides freely in one direction, whatever direction it's rolling on. So the ground, in this case, it slides freely left and right, but it doesn't let you don't pass through the ground. So there's a reaction that is perpendicular to the surface the roller is on. So the reaction is perpendicular to surface the roller is on. So that means there's a reaction like this. We can call it, if that was point A, we can call it AY. Or we can call it RY for a reaction in that Y direction or something. I don't know. We'll call it AY. The pin, if you think about something being pinned, so the roller here lets the beam move this direction, but it doesn't let it move this direction. Technically, it could move up, but we're pushing down on it. The pin, however, doesn't roll, so it doesn't let things move left and right or up and down. It does let them still rotate, though. So it doesn't keep it from doing that, but it does have reactions that make it where the thing it's pinned to can't move in the Y direction, and it can't move in the X direction. So that means it has reactions opposing any kind of potential movement in those directions. So a pin has two orthogonal to each other reactions. And so I did X and Y. They don't have to be horizontal and vertical. They just need to be perpendicular to each other. All right. At this point, I don't have a complete free body diagram because I don't have a coordinate system. So let's put X and Y. Now I've got a free body diagram. I've got all the external reactions, the pin reactions and the roller reactions. They're accounted for. I've got the body isolated in space. I've got a coordinate system. I've got some dimensions and variable names. I've got all the things I need for a free body diagram. So at this point, we would be able to apply our equilibrium equations, assuming we knew that this little beam was in equilibrium. And in statics, it's going to be in equilibrium. So that means I have this equation and this equation. Technically, I have the Z equation also, but I don't have any direction in the Z. I'm not using Z-directed forces. So the equation summation of forces in X does give me some information. It says that, well, BX is the only thing in the X direction, so BX equals 0. And that's fine. Maybe if I had angled this force so that it has an X component, then BX would have a job to do. But if this is just going perfectly straight up and down, then BX doesn't do anything. FY tells me that AY plus BY minus 250 pounds equals 0. So that's kind of useful. But it doesn't tell me the value of AY and BY. It just tells me that they are adding to 250 pounds. Z doesn't tell me anything. It just says that forces in Z, there are no forces in the Z direction. 0 equals 0 is all it tells me. Doesn't really tell me anything. So it doesn't give me enough information. These three equilibrium equations that are based on just translating. They don't tell me enough to let me solve for AY and BY. They let me solve for BX in this case, but not AY and BY. So I need that other equilibrium equation, and that's where the moments come in. So not only do I know that this beam is not moving in X, it's not moving in Y, and it's not moving in Z, I also know that it's not rotating about any point. It's not doing something like this. And that's what the moments are telling me. The moment equation says that this object, if I write summation of moments equals 0, then that means that the object isn't rotating about any point. So these are talking about translating. And this one is talking about rotating. And I know that this thing in my local coordinate system is not rotating around any point. maybe it's rotating about the center of the earth and rotating about the sun and all these other points that don't matter to me right here. But right here, it's not rotating about any of these points. So how I use the equation is I pick a point, any point. I can pick this point. I can pick the point in the middle of this pin or the point in the middle of this roller. I can put any point that I can see in my local coordinate system that this thing is not rotating about. I pick that point. So there's a little bit of like which point to pick. A lot of times it is best, and 80% of the time, 80% of the time, it is best to pick this point to be wherever that pin is. So I've got a pin and a roller. So let's just pick this point. It's not guaranteed, but if you don't have a better plan, then pick the point where the pin is. So to do that, I say that the summation of moments about the pin, which I labeled B, so I'm going to call that point B, and here would be A. So the summation of moments about point B equals 0. So what that means is that this is point B. This beam isn't doing this. It's not doing that. So for that to be true, I have to calculate all the moments about B, and they have to balance. Just like forces in X have to balance, and forces in Y have to balance. There is one other thing I need to do. So it's kind of easier when I'm drawing an X-axis and a Y-axis. There's positive X is going to the right, positive Y is going up because I drew the arrows that way. For moments, you have two options. You have clockwise about point B, so that way, and I have counterclockwise, this way. That's harder to, always know which way you're going to choose. So what you do is you pick and draw on your equation. I'm going to consider you draw a clockwise arrow. I'm going to consider clockwise to be positive. Or maybe you want counterclockwise to be positive. A lot of engineering uses counterclockwise positive. So you draw a counterclockwise arrow and put a little plus sign in there, and that tells the reader that, for this equation, any counterclockwise moments are going to be assigned positive signs, and clockwise moments are going to be negative signs. So it's the same thing as drawing the x-axis going to the right. That tells you that any forces going to the right are positive, and any forces going to the left are negative. All right, so now how do we write a moment equation? So first, a moment is equal to or defined as a torque. So in physics, everything like this is just called a torque. And in engineering, we use torque to mean a specific thing, like you've got a shaft involved and you're transmitting power of some sort. And we use moment for everything else. They're the same thing, though. They are both a force times a distance. And maybe I should write the times this way because it's more like a cross product. And we'll write it that way. What we're going to do, and you could use vector math to do this, but again, we're just using X, Y, Z coordinates components. So what we're going to do is that we're going to say that the force is perpendicular to the distance. So in our little setup here, I'm taking point B as my point that I know that there's no moments about, and I'm going to take every force on the free body diagram, AY, BY, BX, and the 250 pounds, and I'm going to calculate what moment did they create about B by multiplying that force, AY, BY, BX, or 250 pounds, times their distance from B. So, start with AY. AY has a line of action that is vertical, and I said that the force and the distance have to be perpendicular to each other. So if the force has a vertical line of action, perpendicular to that is horizontal. So the horizontal distance between the line of action for AY, this and point B is 9 feet. So I multiply AY times 9 feet. Then I have to say if this term is positive or negative. I said, for my equation, I said that counterclockwise moments, so moments that would cause the body to rotate counterclockwise about the point of interest, are going to be positive. Counterclockwise ones are. Clockwise ones will be negative. So we go over here. This pin, I drew the arrow pointing up, which would make the body, the beam, rotate clockwise about point B. So according to my equation, this needs a negative sign on it because I said counterclockwise was positive, and this is going clockwise. All right. The 250 pounds, it also has a vertical line of action. It has a moment arm. That's what you'd call the distance between, when the distance is perpendicular to the force, remember that? That distance is called a moment arm. So it has a moment arm of just 3 feet. So I take the 250 times 3 feet. I got to decide if that term is positive or negative. So let's go back to horizontal here. The force, 250 pounds, is pushing this way. That goes around counterclockwise. The body moves counterclockwise around point B. I said that counterclockwise was a positive term, so this gets a positive term. BY has a line of action that's vertical, but the line of action actually goes through point B. So if I were to take and multiply BY times the distance between its line of action and point B, that's 0. That's kind of like you're trying to open a door, but instead of pushing on the door knob, you're pushing on the hinges. And, you know, the door doesn't move because you don't have any distance away from those hinges to actually cause it to rotate about them. So BY actually doesn't create a moment about B. You could go to your deal here. Here's B over here. I'm going to push here, and well, I kind of missed. But if I push here, then no matter how hard I push in this direction, the body doesn't rotate about point B. BX is a little bit trickier, but only because of the way I drew it. So I drew it, you know, there's a tiny little distance the way I drew it, and it would probably have been better if I had drawn it like that, where it's more obvious that BX is just doing this, where I'm pushing here and there's no rotation. So I'm pushing here and doesn't cause any moment. So BX does not cause a moment. So BX and BY do not cause moments about point B. That is the reason, or the generally good approach of using the pin, because you know it has two unknown values there, the X and Y reactions at the pin, and you don't have to worry about those two unknowns showing up in your equation. So the only unknown in my equation is AY. The rest of the equal sign here is equals 0. So these two moments, AY times 9 feet, 250 pounds times 3 feet, have to balance each other. And if I solve this equation, AY will equal, gotta find one, here's my calculator, 250 times 3 divided by 9, 83.3. The units would be pounds, and the sign for that would be positive. So the positive sign on this number means that I chose this arrow to be drawn correctly. I drew it in the right way. So it's pointing up. And then once I know that, now the X equation suddenly becomes valuable, because I can plug in, oh, AY is 83.3 pounds plus BY minus 250 pounds equals 0. Therefore, BY equals 166.7 pounds. So now, using this idea of summation of moments, I've gotten all of my equations answered. And you'll notice I had three unknowns, AY, BY, BX. I used 1, 2, 3 equations. The Z equation actually just said, it just gave me an identity, so it didn't actually give me any information. So I used those 3 equations to solve for the 3 unknowns in my free body diagram. We'll keep adding, there are other little details to add into this moment idea. But for now, like for one, we need to do 3-dimensional moments someday. And what if the forces are at angles? How do we deal with that? And we'll deal with that when we get to it. For now, we just need this little bit of intro. Okay. Don't see any questions. So let's go into our truss. So let's rebuild our truss over here. So this is the simplest truss that we could create. One that just has one force on it somewhere. Remember, the force has to be at a joint. And 2 supports of some sort. So a pin and a roller. Why we use a roller is, why not just 2 pins? So that's more of a practical thing. One, if you just look at the math. So if I look at the math and I had a pin at A, like in this picture, if there was a pin at A, then I would need an AX and suddenly have 4 unknowns. So that's a little bit of a problem. But in the real world, what happens if I put 2 pins here and this structure is made of metal and it heats up or cools down, that metal expands or contracts. And if I have locked both of these down and this piece wants to expand, it has nowhere to go. So it will buckle, it'll create new stresses that I didn't account for in the piece because it wants to get longer, but it can't. Or it gets cold and it wants to shrink and it can't. So you really do have these type of fixtures in trusses just so that there's some allowance for changes in size due to temperature changes. If you ever drive across a bridge and you hear that periodic thumping sound, it's because there are expansion joints in the bridge that are doing this exact thing. They're not necessarily rollers with wheels and everything, but they're a way for that piece of the bridge to change its length a little bit, so without having to like crash into the next piece of bridge and buckle or tear it apart or something. So it might seem weird that we put wheels on one end of our truss and not on the other end. But there are practical reasons of why you want to at least model it that way. Whether or not you literally put wheels on the bridge is different. You probably don't. You probably put some allowance for expansion and contraction. And we model it as a roller. All right, let's go back over here and draw our little truss. A picture of our truss. So I'm going to draw it. It's kind of like this. Oh well, let's make it a little straighter than that. Normally, when you're labeling these joints, you do it alphabetically, and I usually start in the left corner with A, and then go around, clockwise alphabetically. So A, B, and C. And you do that so that now you can use those 2 letters that are at the end of each one of the truss members. Remember, each member only has 2 joints. So there's 2 letters, and you can name the member that way. So remember, this is member AB. And this one is BC. And this one is AC. Normally you alphabetize the letters. So you could say CA, but normally you alphabetize them. I don't think it's going to be a big problem if you don't alphabetize them, though. We have a roller over here. We have a pin over here. And we have our force here. So we followed all of the rules for a truss. Each member only has 2 pins. There are 3 external reactions. I didn't really write that down as a rule up here, but that is going to be true. There are going to be 3 external reactions, 2 at the pin and 1 at the roller. We have applied the external forces at the joint, so we only have the 1 external force shown. We're going to have 2 other external forces, the 2 reactions, but they're also going to be at pins or at joints A and C. So let's take this thing. This is not a free body diagram. Actually, let's go ahead and let's copy it. One thing. Oh wow! I somehow erased part of it. Let's put that back. One thing that sometimes you're in a hurry and you don't want to draw these things over and over again, and you might think, I'll just take this picture, I've drawn the sketch, and then I'll just draw the roller reactions and the pin reactions right here. And that's probably fine to do when you're in a hurry and just trying to get that solved, but it's not okay to do that in an actual proper solution, because now you're working on this bridge and you're doing this to try and get your first pass at the member forces and all the pieces of the bridge, and you do this, and somebody comes along later and looks at it and they're like, well, you've got these external forces at the roller and the pin, but what about the reactions at the roller and the pin? Because what you've done with this picture makes it look like these are forces in addition to the forces from the pin and the roller. That's not at all what you meant when you were quickly doing this. You meant those are the reaction forces, but what you're showing is you're showing the pin, and then you're showing these other forces. So it kind of implies that there are some forces on top of the reaction forces. And so it gets confusing, and it's best if you're doing one of these for a real solution and not just quickly for your own doing, it's best to redraw it and remove the pin and then put the pin reactions. So this is CX and CY. Remove the roller and put the roller reactions, AY. Otherwise, you could confuse somebody. You could even, if you come back to it hours later, you could confuse your own self potentially. Let's put some dimensions. Let's see. This is kind of 1, 2, 3, 4, 5, 6, 7-ish somethings, feet we'll say. And then this 1, 2, 3, 4, 5-ish or so. And that's kind of all the dimensions we need. We can put a coordinate system in here if we just want one. Okay, now we've got a full-blown free body diagram as soon as we put some force value on that arrow. Now we've got something we can work with. Okay, so when you're solving a truss, the first thing to do is, not all the time, there can be shortcuts that you can take, but most of the time, or if you're unsure, then the first thing to do is to solve for the external reactions. Or, well, the first thing to do is draw the free body diagram of the truss. FBD is free body diagram. So that's the first thing. So we did that. Then, 90-something% of the time, solve for your pin and roller reactions. There are some instances, the 10% of the time, where you can see a solution path. You only need to know one thing maybe, and you can see a solution path where you don't need to solve for the reactions, and that's fine. But if you don't see that, or if it doesn't exist, then you're going to do the pin and roller reactions next. So let's do that with ours. So the pin and roller reactions, normally the best thing to do summation of moments about the pin. So the pin for me is C. Let's do clockwise as positive this time, just to show that you can do either one, whichever you prefer. So I've got summation of moments about C equals 0. So just to make certain we're certain about all this, that means that here's C, and this truss isn't doing this. Not doing any of that stuff. All right. So here, CX and CY, obviously they're called C because they're at point C, so their lines of actions go through point C, so they don't create moments about point C. So I can leave those out. So I'm only left with AY and the 500 pounds. So let's do AY. It is a vertical force, so I need the horizontal distance between AY's line of action here and point C here, which is just 7 feet. All right, feet. That force is going to create a clockwise moment. So if this force was allowed to control the rotation, I'm pushing up, it's going to make the whole body rotate clockwise about point C. So I give it a plus because I said clockwise is positive. The 500 pounds has a line of action that's also vertical. Its moment arm is only right here. Now, I didn't technically give quite enough information on this problem to know what this green moment arm is, but we can assume that all of these pieces are, well, these two are the same length, and the distance from this line of action over to here is half of this span. But technically, it could be different than that. You know, you'd really need another piece of information to verify that. We're going to assume that this truss is symmetric about its, it has bilateral symmetry. So that makes this moment arm 3.5 feet. And this force, we're pinned at C, or our equation is assuming that we're pinned at C, and we push down, it would make the body rotate counterclockwise about point C. And in this equation, whoops, I don't think I showed you that. So pushing down at where this force was applied goes counterclockwise. And I said that clockwise is positive, so counterclockwise has to be negative. And those are the only forces that create moments about C. So they equal 0. And I can solve for AY. So 500 times 3.5 divided by 7 is 250. Now all of that, oh, well, let's do therefore. Therefore, AY equals a positive 250 pounds. The positive on this number means that I drew AY in the correct orientation. Now, we could have, as soon as we saw that the truss was symmetric and the loading and supports were symmetric, we could have known that AY and CY are just half of the 500 pounds. So it is okay to do things by observation. Just I'm not yet, because I don't want to skip too many steps. And it is nice to be able to show that it works even when you do the math. So there's AY. We could write summation of forces. If we do summation of forces in X direction, that will tell us CX equals 0. So that's useful because that means that we don't have to worry with CX. Again, whoops, where'd my pen go? It's underneath there. If this force had been at some angle, now CX has a job to do, because it has to react the X component of the force if this force has some X component. But if it's vertical and with no X component, then this one does not need to react. This one can't react. It's the roller, so it can't react X direction because it's freely rolling on the X ground down here. So our other equation, summation of forces in the Y direction equals 0. We have AY. And what I like to do, even though I just solved for AY, I like to write the equation based on the free body diagram and then fill in all the variables. That way I don't miss a sign or something like that. Maybe I solve for this AY and it's actually negative and I forget to put the negative on there or something. AY plus CY minus 500 pounds equals 0. Then I plug in, oh, AY is positive 250. So 250 plus CY minus 500 pounds, or, well, I said minus and wrote equals. Minus 500 pounds equals 0. Therefore, CY is also a positive 250 pounds. So it's much faster when you're not writing every one of these. You know, we could have just looked at this one and said, oh, CX is 0, AY and CY are both 250 and be done with it. But obviously there will be some on exams and quizzes that are more complicated than that. So I'm doing all the steps for now, and I probably will do all the steps for even later too. But just so we don't skip anything. Okay, we still got plenty of time. What we need to do now is actually solve the truss. So all we've done so far is solve for the reactions on the truss. So we know what forces are being applied to the truss by the 500 pounds and by all the external reactions. We know all that now. But what we really want to know most of the time when we're dealing with a truss is what's happening to all the members of the truss. So what's happening to member AB and what's happening to member BC and AC. Because if we know what's happening to them, then we can start to design them. You know, oh, well, AB has this much force in it, so we need to make it this big so that it doesn't tear apart or crush or something like that. So we can use those material properties and the stress and even strain equations to help design the truss members. But we need to know how much force they have to deal with. So that's where this next step comes in. And this is called the method of joints for trusses. And a lot of times it'll just be MOJ. And then it's for trusses. So we will have later, in a few weeks, we'll have structures that look like trusses, you know, look like this, but they've got some other force on them somehow that makes it not a truss. You know, this force being applied to this member makes this member not a two-force member, and therefore this isn't a truss anymore. So it's a frame, and I have to use a different solution procedure to solve it. And I can't use method of joints once I decide that it's not a truss. So this is method of joints for trusses. So what method of joints means is that you individually look at every joint of the truss and treat each of those joints as a concurrent force system, and you solve your equilibrium equations just with summation of forces in X or Y, or Z if you have a three-dimensional truss. So method of joints for trusses is each joint is analyzed as a, and then for us it's going to be 2D concurrent force system, although it can be 3D if you had a three-dimensional truss. So what that means is a couple of things. It means that you need to pick a joint, or to start with, where you know at least one value. Now, in our truss right here, every joint has one known value at least. Joint A has AY known. Joint B has 500 pounds known. And joint C has CX and CY known. So I could start at any of these joints. But a lot of times, you know, you'll have more members in the truss. And so some of these wouldn't be good starting points. So in this case, though, we could start at any of these. So if you pick a joint where there's at least one known, and then of those, pick a joint with, whoops, that's not with only 2 unknowns. Now, sometimes this isn't possible, and you have to kind of skip around or do things simultaneously. But what this is getting at is that you only have 2 equations that you're going to work with. So if you only have 2 equations, then you kind of only can use 2 unknowns. So in our case, this is fine because all of the joints only have 2 unknowns. So joint A has the force in AB and AC connected to it, and they're unknown. At joint B, AB and BC are unknown. At joint C, BC and AC are unknown. So in this simple truss, we could have started anywhere. Other trusses, they're going to have more than 2 members connected to them, and so there might be some places where you just can't start at a certain point because there's too many unknowns, or at least it's better if you start at another point. This is also why you solve the external reactions first, is so that you have some known values. But it is possible that you don't need to. Like I said, 90% of the time you do need to, and 10% you don't. All right, so once we've done that, draw a free body diagram of the chosen joint. Let's start at joint A. So the free body diagram of joint A is just a dot or a circle, or it's nothing fancy. And then we need to put all the forces that are on A. So we found AY, and it was 250 pounds. And we have AB and AC. Now, if we go all the way back to here, part number 5 here says that each member in a truss is a 2-force member. And I don't have to draw the AX, AY type reactions for the member. I can just draw the force or the tension or the compression or whatever I want to call it. I'll probably call it force in that member along its line of action. I don't necessarily know if it's tension or compression unless I'm good at looking at the truss and just telling. But what I'm going to do, and you don't have to do it this way, but you do have to draw the arrow somehow, is I'm going to start, even though I know it's wrong, I'm going to start with all the forces drawn as tensile forces. So that means they're going away from the body. So I'm just going to draw this as the force in AC and draw this as the force in AB. So arrows going away from the body of interest, in the free body, equal tensile. So what I'm doing by drawing AB and AC pointing away is I'm assuming that those members, AB and AC, are in tension. I know good and well that the entire truss cannot be in tension. Some of it has to be in compression somewhere. But maybe I'm not ready to try and mentally figure out which is which. So I'm just going to draw them all in tension. In other words, I'm not going to spend a whole lot of time trying to figure out ahead of time if it's tension or compression. What I'm going to do is I'm going to set up the equations and let the math tell me which ones are tension and compression. So all of the ones that come out positive means that I drew the arrow the right way and there were tension. And anything that comes out negative means I drew the arrow the wrong way and it was a compressive force. Let's see. We need some of these dimensions because I need to know something about this angle. What I'm going to do is I'm going to put the rise over run. So the run for this was 3.5 and the rise was 5. If I go back to here. So the rise of 5 and the run is half of 7, so 3.5. Whoops, went too far. All right. I can put the coordinate system in here just to, have X and Y. Now I've got my free body diagram of joint A. It has all the forces applied to A that were there. Well, basically what I'm doing is I'm taking this, that out and putting all the member forces. So this was touching it, this was touching it, and this was touching it. I'm replacing all of those contacts with forces, with these arrows that I've drawn on the free body diagram. Then I'm going to take my free body diagram and apply my 2D equilibrium equations, so the X and Y. And it probably is worth it to spend a few seconds looking and seeing which one you should do first. So for instance, if I did summation of forces in the X direction first, it would say that AC is in the X direction and AB also has an X component. So there's two unknowns. In the Y direction, there's only one unknown, the Y component of AB. So in this case, it's better to start with the summation of forces in the Y direction. It doesn't actually hurt anything if you do X first. It just gives you an equation you can't solve right away. Then you write the Y, and then you can go back and solve the X. So it doesn't really hurt. Or you could just decide, I'm going to do them all simultaneously anyway, so it doesn't matter. So whatever is better for you. So summation of forces in the Y direction. I've got 250 pounds. I've got plus because it's the Y component of AB is going upwards. I am going to use the definition of the sine. So first let me get the hypotenuse of this little blue triangle. 5 squared plus 3.5 squared. Square root of that is 6.1. So remember, sine of an angle is equal to the opposite side over the adjacent side of that angle. So instead of doing, and you could do it this way, you could calculate the angle alpha, you could calculate that angle and figure out the opposite and adjacent sides and all that, and you could figure out what alpha equals, and then you could plug in the sine of alpha in your equation. You could do that totally fine, but I know that, well, the sine of alpha, according to my diagram here, equals the opposite side, which is, oh, I said opposite over adjacent. That should be opposite over hypotenuse. Sorry about that. So the sine of alpha equals opposite over hypotenuse. So I have 5 as the opposite side, 6.1 as the hypotenuse. 5 divided by 6.1 is 0.8197, and that value is the sine of alpha. So why calculate alpha just to return that value to me? So what I'm going to do is when I write this equation, I'm going to write FAB times sine of alpha, except instead of writing sine of alpha, I'm going to say that, oh, sine of alpha is 0.8197. Or, if you don't like the decimals, you could write it, oh, the sine of alpha is the opposite side over the hypotenuse, whatever units these are. And so you don't have to go and calculate the angle. It's the whole point of that. So that is a completely legitimate way to do it if you want to. So what happens here is I can solve for AB. And it ends up being plugging numbers in 305, but it's negative. So the negative sign, remember, means that I drew the AB arrow, I drew it the wrong way. So I drew it in tension. It should be going the other way, so it should be compression. It's generally not best to leave this as FAB equals positive or negative anything. It's usually best to write it as FAB equals 305 pounds and then put a C or a T after it to signify tension or compression. compression or tension. I think I said C or T. So, because somebody else might not have assigned positive and negative arrows the way that you did, and their negatives might be tension. So it's better to write T or C so that you're unambiguous about what you mean. So this is the actual answer for AB. 305 pounds of compression. Now we can do X. And again, what I would do is I would go back to the diagram and write, all right, AC times FAB times, and now I'd use the cosine, which is the adjacent, so 3.5 over the hypotenuse 6.1. The 250 has no X component, so I leave it out. Equals 0. Then I go in and say, oh, this AB is 305 pounds of compression. I don't know why I put times there. That should be plus. 305 pounds of compression. So this is where you have to decide what you're going to do with tension and compression. And this is why I decide that I'm always going to draw all my arrows in tension. That way I know that compression numbers are always going to be negative values. And tension numbers are always going to be positive values, but you do have to get these arrows the right way in your mind. Not necessarily, you don't necessarily have to redraw them on paper, but if that helps you, maybe you should do that. But you just need a system for you that keeps these arrows in positive and negative related to tension and compression all consistent. As long as it's all consistent, you'll be all right. So what we need to do is we need to plug in a value for FAB. So FAB, I have drawn it going up and to the right, but actually it goes down and to the left. So it has a negative X component. So somehow I need to know that. And for me, what I do is that's where I plug in my negative value. But you just need whatever system makes the most sense to you. Mine may be cumbersome to you. I don't know. Now we can solve for AC. And it's going to come out positive, right? Because we have a negative number here. Move it to the other side of the equal sign, it becomes positive. So 305 times 3.5 divided by 6.1 is 175. And then for our actual answer, we won't rely on positive or negative. We'll rely on T's and C's. All right. Now, in this particular truss, we know that by symmetry, we have symmetric geometry. We have symmetric loading. Technically, there's this CX over here that's not on A, but we decided that CX is 0. And we have symmetric external forces. So when you have that, then once you've solved half of the truss, the mirror image half is the same value. So AB and BC are the same value. If you don't know that or you're not sure, then either go to joint B or joint C and set up method of joints at that one and solve for that. In this case, you would get AB is 305 pounds of compression. You would get that BC is also 305 pounds of compression. Okay, let's talk about one last new thing, and then I will hand you off to do some web work. We'll come back next time and do some more truss problems. We'll spend a little bit of time on trusses. But this next topic is early on, when I was talking about the two force members, I mentioned that every member in a truss is a two force member, with the exception of these oddball zero force members. So what this does is zero force member does mean that when you run through the math, you draw the free body diagram and you run through the math, you will calculate that this member has 0 force in it. So an easy one to think about would be, let's take the same truss that we just had. And let's add a piece to it right through the center. So we're going to add this piece. So now we've got member or joint A, B, C, and we've added this joint D. Now, so this does mean that AD and D, I did draw that as one long piece, but AD and DC are actually 2 separate pieces. So even though I drew it as one long piece, I just was being, quick on my drawing. But technically, AD is one piece, and then a separate piece is DC or CD. All right, let's go ahead and put our, let's put our force up here. Reaction force, reaction force, reaction force. We don't need dimensions for this. So if we were to look at joint D, method of joints at joint D, I've got force CD. I've got force AD. And I've got force BD. Whoops. Force BD. Okay. And I apply my equilibrium equations, my 2D equilibrium equations. Summation of forces in the x direction equals 0. Again, I'm not really worried about the numbers that these equal, but my equation would say FAD equals FCD. So that's fine. But when I write summation of forces in the y direction equals 0, I get FBD equals, there's no forces in the y direction except it. So it equals 0. So force BD, even though there's a piece right here, it's actually a 0 force member. If you want to draw it as a little dotted line. So it's even so much that there's a force that looks like it's pointing directly on BD, an external force, but the equations clearly say that if I add the forces in the y direction at joint D, that BD has to be 0. Now, as soon as AD and CD are not parallel to each other, or not collinear with each other, maybe the truss deforms a little bit, and I've got something like this. Now, it may not be much, but there is something for BD to do. It does have other forces in the y direction. So as soon as it becomes non-collinear, AD and DC, as soon as they're non-collinear, then BD does have some amount of force it has to deal with. Summation of forces in the y direction equals 0 says that FBD is equal to the y components. I'm not worried about the actual math of AD plus CD. Right? So it's not 0 anymore. It might be a small number, but it's not 0. So it would be handy if you could just look at a truss and follow some rules and identify 0 force members. So here are those rules for finding 0 force members by observation. Obviously, you can calculate it and it just comes out 0, and that's one way to do it. But we might want to find 0 force members by observation. So the first thing you do is look for a joint with 3 members. So Joint A has 2, joint B has 3, C has 2, D has 3. So B and D both have 3 members. 2 of these members need to be collinear. So they don't have to be horizontal or vertical or any particular orientation. They just need to be collinear. Their lines of actions need to overlap. So B, none of those, AB, BD, and BC, none of those are collinear. But at D, AD and CD are collinear. So next, make sure there is no external force applied at this joint. And it's got to be an external force. And this joint. So at D, there's no external force at D. Now, if you look at the member BD, yes, the other end, at B, there is an external force. But at D, the one I'm interested in, the one I'm observing right now, there's no external force at D. There's only the internal forces AD, BD, and CD. So if these 3 things are true, so if 1 through 3 are true, the third member, or the non-collinear member, we would write it that way, is a zero force member. Meaning that if you were to write the equations for summation of forces in X or Y at that joint, one of those equations will tell you that that third member is 0. It has 0 force. The other thing is that a lot of times in the drawings and the examples, that third member is perpendicular to the 2 collinear members. That's not necessarily true. It can be at any angle. It's just easier to show with the equations when it's perpendicular, but it could be at any angle and still be a 0 force member. Because, if we had done BD instead of this way, we had done it this way, when we go to do the Y component, it's still the only thing that has a Y component. So there's no way to balance its Y component, no matter what angle it's at. So just because it may not be perpendicular doesn't mean that it's not a 0 force member. Okay? Here's a bonus rule. If 2 members are connected, and if only 2 members are connected and there is no external force at that connection, well, what am I writing? There is no external force at that joint, both are 0 force members. So like this, if I have a truss and, I don't know, let's just draw some truss over here. This is our truss, we'll say. And we've got forces here, here, maybe something over here, something over here. This is our setup. Then these 2, here and here, they are connected at joint A, B, C, D, joint E. So, but there's no external force there at E, so both DE and EF are 0 force members. So essentially, you could take them out of the truss as long as it's loaded this way, and the truss would behave the same, more or less. Now, these zero force members, for one thing, it's not like they're completely useless, because if the truss does deform, like we did in this picture, then they do carry a load. So a lot of times when we're analyzing it, we're looking at everything perfectly rigid and not deforming. But they do carry a load when things are deformed. Or we're looking at one particular loading scenario. This truss might have to be loaded a lot of different ways. And so under one scenario, there may be no force on those members, but under another scenario, there may be a force over there, and now suddenly they are carrying a load. So you have to remember that. And they help with stability. Sometimes they help with aesthetics. They just look right to be in that position. But a lot of times they do have functions, but maybe under the exact loadings that you're analyzing for that one problem, they don't have a large role to play. So it's not like you can just take them out all the time. But you can, like, for that problem that you're working on, if you find a zero force member, you can take them out of your analysis. As long as you don't change the loading situation somewhere halfway through, then you can take them out and just automatically know that they are zero force members. The other thing, one last thing on this, is that once you find a zero force member, you should go back to step 1. So I'll write maybe down here, number 5. Once you find a zero force member, remove it, maybe make it a dotted line or circle it, something to make you remember that it's a zero force member. And go back to step 1. Because now there might be, since you removed it from the truss, there might be a new joint that once had 4 members, but now you've taken one out and it only has 3 members, and you might find another zero force member there. So it could create a chain reaction of finding zero force members. All right. I think that is the intro to trusses. A little bit of 2 force members, zero force members, a little bit of moments. I think you've got enough now to where you can solve really basic trusses with method of joints. I've opened up homework 7, which is that it's some of the problems there get more complicated towards the end, but the first ones are pretty straightforward, not much more complicated than this truss that we looked at here. And you should be able to work through those method of joints wise, because method of joints is really just 2D concurrent force systems. And then you do have to be able to solve external reactions. Going to need to be able to do that for all the stuff we're doing from here on out. And I think you can work you have a week to work all of homework 7, but you should start on it. Wednesday we'll come back. We'll do some more trusses. We'll introduce a new method in addition to the method of joints, and carry on with it. All right, but I think that's enough for today. We're a few more minutes before we officially run out of time, but I think we've got plenty done today. I will see y'all on Wednesday.